Hello, my students. Well, I'm stuck here at home till Tuesday. This is the lesson I would have given you today. A little bit of a review of where we're at. We have a new force, or a new formula for force, the electrostatic force between two charges. It's going to be K Q1 Q2 over R squared, where that is 9 times 10 to the ninth. You know where you find that? First page of the reference sheet that you've already printed out. That's Coulomb's law constant. On the reference sheet, it's actually going to look like this. K is going to be written as 1 over 4 pi epsilon naught Q1 Q2 over R squared. We're just going to plug in the permittivity of free space into here because that's what we're going to be using, and you end up getting 9 times 10 to the ninth when you do that math. And again, page 1 of your reference sheet. There's the permittivity of free space. Plug it into here, you're going to get 9 times 10 to the ninth. Then we defined electric field strength as the force felt on a charge you put in it. And then if you plug in the force felt on a charge put in it, that is an electrostatic force, you then end up with KQ over R squared. So this, since you have a little q there, this is a good way to figure out what the electric field is any given distance away from a point charge. Really applicable to point charges. And these are, once again, listed on the reference sheet. We have done all of this. We are now starting over here. We're going to be using everything down through the top 5 for this, for static electricity. And wherever it says 1 over 4 pi epsilon naught, we're just going to use K because we're not going to change the medium that we're putting these fields up in. Then we decided we were going to define what electrical potential is. All right, listed over here as voltage, electrical potential, or potential difference, or voltage. There's 3 ways to say the same thing, really. That was going to be the work done per charge that voltage produces. So like if it was an outlet, a wall outlet, for every coulomb of charge that came out of the wall outlet, it can do 120 joules of work. Since work is force times distance, you'll plug in, once again, Fe right down here. You'll get one of the R's to cancel with the D, one of the Q's to cancel, and you end up with KQ over R. So multiple formulas for voltage, potential difference, electrical potential. 2 formulas here for how to figure out the electric field strength of an electric field. And this one was for the force felt between 2 charges. Then we started talking about parallel plate capacitors. If you have one plate over here, and another one parallel to it, draw it as best I can 3-dimensionally, and you hook up a battery across it. That's our symbol for a source, a battery, a plug, whatever it is, a source of electricity or potential difference. This would be your voltage, whatever it is, 9-volt battery, 12-volt, an outlet's 120 volts. You should remember that the small side of that symbol for a battery is the negative side, and the larger side is the positive side. That allows you to say, okay, well, all the negatives are going to be attracted to that, leaving a highly positively charged plate over here. And it's going to then push negatives into this side. What happens is, instead of having like a radially outward field line, like on point charges, this develops into parallel electric field lines. And since if you put a little positive charge in there, That defines our direction. It would be pushed away from the positives towards the negatives. So all your field lines are equal and going that way. Because they're parallel, that makes this a uniform field. It's the same strength everywhere. Last formula to remember about this, to figure out the electric field inside of two parallel plates, you would have to divide the potential difference by the distance between them. And that's where we kind of left off in class. Distance between them is this, from here to here. Distance between the plates. All right, real convenient way to figure out electric field strength, because that's going to be a known. It's whatever's on the battery, the source, and you can measure that distance evenly. So that's kind of where we left it. And the 8th period class saw this, but the 4th period class did not. I did an example where I put 4 charges in a perfect, as best I can, I'm drawing this as a perfect square. And I asked a couple of questions about this point right dead smack in the middle. And since it's a perfect square, this is going to be distance D. Call it D, call it R, call it whatever you want. It's just distance D. And that's going to be the same for everybody. And my question is 2 parts. Find the net electric field at the dead center and find the electric potential at the dead center. Now, this one's a vector, this one's a scalar. But the rules kind of change on this. Instead of taking care of your sign on the vector problem, because if positive's right and negative's left, it doesn't quite apply to this, because when you do the math, you're going to end up with sometimes a negative electric field line actually works with one that's positive, and you have to add them together where you think you might want to subtract them. So let's just go through one together. I'm just going to make up some charges here. We're going to see this is charge 3Q. I'm going to make this negative 2Q. 4Q, and just plain old Q. Okay? That's the setup. Each individual charge has an electric field value dead center. You've just got to add them all up using vector addition to figure out what the net leftover electric field is. Let's just I'll do this one. Let me just circle this in red. Red one here and a red one here. So to figure out the direction of that field, put a little positive test charge there. Since that's positive, it's going to push it away. The electric field due to the 3Q charge right here is pointing right towards the 4Q because it's a square. I've set that up. Now looking at the 4Q, that's positive also. If that's positive and that's a positive test charge, they're going to repel. It's going to push it that way. They actually work against each other. They'll have to be subtracted when we put this all together. Now looking at the other 2 corners, here you've got a negative 2Q charge. This is a positive. That means the field lines due to this guy is up to the right, pointing right towards 2Q. This one, since it's a positive, it would push. I shouldn't say push, but its electric field direction would be up and to the right. So these 2 work together. Even though if you did the math, they'd have opposite signs, it looked like they subtract, you'd be wrong. That's why I leave the negatives out of calculating these values and just look at your drawing in the end. These 2 guys are going to add up. The 2 red ones are going to oppose each other. They'll be subtracted out. So the formula for electric field strength with a point charge is KQ over R squared. So for this one, 3Q, I'm going to pull the 3 out to the front. Just makes me happy to do that. 3KQ over, I called this distance D squared. That's what this arrow's magnitude is. Now let me do this guy, which is what this arrow's magnitude is going to be. That's going to end up being 4kq over d squared. So when you add these up, they're in opposite directions. They actually subtract from each other. You end up with this guy winning, pushing up that way just a little bit. The electric field strength due to this guy and this guy is up and to the left because the 4K wins the battle. It's the bigger of them, and it's just going to be 1kq over d squared. So all we've done was figure out what the field is due to these two guys. Now we'll do the other corners along this axis. They're going to add together. Even though there's a negative there, I'm not going to put it there. That's going to be 2kq over d squared. This one's just going to be 1kq over d squared. They work together, so you add them up. That means you're going to get a 3kq over d squared vector going that way. Now that, my friends, is a right triangle. Oops. Spin it around like this. Maybe you can see it a little better. Right triangle. If this is a side and that's a side, the resultant vector is a vector drawn from the tip of the first to the tail of the last. You've just got to figure out what that side is. I'm going to redraw that over here, just a little bit bigger. You have up and to the left with kq over d squared. You have one 3 times the size of that, which is 3kq over d squared. You want to find the resultant or the hypotenuse. Got to use a little Pythagorean theorem to find that. So this side would equal the square root of 3kq over d squared, all squared, plus kq over d squared, all squared. So when you do the math and square all that stuff out, 3 squared is 9. You would get the square root of 9k squared q squared over d to the 4th plus k squared q squared over d to the 4th. Well, that gives you a total of 10 k squared q squared over d to the 4th. Then take everything's in the radical. That'll end up being square root of 10 kq over d squared. That's the net electric field, and it's up and to the right. I could ask you for an angle like this if I gave you numbers, but that's how you do it.